So can you see this screen?
Yes, sir.
Okay.
Sir,
Yes.
at the differential amplifier also used in feedback loop.
What?
In loops, like to subtract the source signal from the feedback signal from the output.
Differential amplifier with feedback.
No, sir. Just like in a feedback loop, but there is a junction where we need to subtract the source signal from the subtract the output signal from the source signal.
The differential amplifiers are used as their main function is to serve the purpose of the mixture at the input side. Take the difference of the two signals. One is the main signal, the other is the feedback signal, right? So the main function of the differential amplifier is to take the difference between these two. Yeah. So that's why op-amp has this input stage as the differential amplifier, right? So their main function is to, the summing up these two signals. And that's why this is so important in the amplifier circuit. So this is our usual or differential amplifier, well-known differential amplifier circuit. And the differential gain for this amplifier. So let's say we are taking the output from this single node, the second collector, And the differential amplifier is defined as, do you remember what is the gain?
So GMRC.
GMRC, yeah,
Oh, half GMRC then.
right, it's half GMRC because we are taking from the single node. It will be half GMRC. Okay, so now this is the gain of the differential amplifier with the what we call RC. RC is the passive load here, right? And it will have the all the limitations of the passive load. Like we cannot achieve very high gain, and with the increase in gain, there will be increase in power losses, and you will need higher the power supply. Right? So we want to replace these RCs with active load. So that is our differential amplifier with active load. Q3, Q4 are basically the current mirror circuit. Together they make the current mirror circuit, and they are working as the active load. Any question, guys?
No, sir.
What will be the gain of this one? No idea.
So GM R naught.
What is unknown?
So the resistance between the collector and the emitter.
The small unknown. Okay, let's see what is the gain. Okay, so to find the gain first, we need to know, what is the load resistance, right? So there's nothing connected, but I just assuming some load resistance here. So what is this load resistance? In the previous circuit, RC was the load resistance, right? RC was working as the load resistance. Now for this one, what will be the load? So that first we need to establish. So there are two output resistances, one coming from this side the other one coming from this side, right? Let's call it R01 and this one R02. Oh my, this is like this. I think this is the problem. Okay, so RL will be, we can take as the parallel combination of R01 and R02. Right? And R01 is R02 and that is R04. Right? And if we assume this both same, then we can write R0 half of R0, assuming that R02 is same as R04 and this same as R0. Okay, guys. Now, let's say if the current flowing here, right, is I naught, then V naught will be I naught RL. And RL is half R naught, so that we can write is what is this current I naught, right? How much is this current I naught? Now, the voltage here, let's say, is VBE, right? No, not VBE, this is VID. Sorry, let me clear it. So that is VID divided by 2, plus on this side, minus on this side. And this also VID by 2, but here plus is on this side, minus on this side. Now, because of this voltage, right, polarity of these two voltages, current here flows down and here flows up, right? That's how the current flows in the differential amplifier. The current here, IC is GMVBE, so that we write GMVB is VID by 2, right? And on this side, it will flow up. There is a negative polarity, but instead of writing negative, we just change the direction and show it like this. So that's how the current will flow. Now, how the current will flow? So this current will flow this way and out into this load resistance. Is that clear? Now, what will be the current here? Right, in this is the collector of Q4. What will be the current in the collector of Q4? So since this is the direction of the arrow in the emitter is in PNP, and so the current will go in this direction, right? So what will be how much current we'll have here? No idea. Since this is a current mirrored circuit, you see the current on this side is GMVID by 2. So same current will be reproduced on this side. And this is the property of the current mirror circuit. So the current here will be also GMVID by 2. And these two currents together, right, they will flow out, right, and then feeding this load resistance RL. So basically we'll have I naught will be GM PID. Right? So basically it doubles the current, right, of the differential amplifier, the current mirror circuit. So you substitute GMPID here, so you get half GMVID or not. So now the gain of this differential amplifier V naught by VID will be half GM R naught. Also, we can write that as GM is IC by VT and VA by VA divided by 2 VT. So that helps to we get a very high gain at the output, right? So VA for VA 100 volt and VT 25 millivolt, right? So you get a gain of about 2000, right? Volt per volt. Any question, guys? Hello.
Yes, sir.
No question. Okay, so this is our differential amplifier with active load, right? Now, as we discussed in your last class, we can have also further modifications, right? We can have different modifications for different levels of gain. We'll show some of those. So what is this circuit?
Codes,
Hmm?
cascode configuration.
What is cascode configuration here? So this part is in cascode configuration. This is the current mirror, right? So this is the current mirror in cascode configuration. So we have the cascode current mirror. Right? So now the cascode current mirror is our active load. Right? Instead of just the basic current mirror, we have the cascode current mirror as the active load. So now what will change is R02 will change, right? R01 remaining same. So now R02, right? So how much will be R02?
Sir, R naught 6 into 1 plus GM 6 parallel R by 6 and R naught 4.
And what will be the end result?
Sir, R naught 6 into 1 plus GM
1 plus GM. In the last class I showed, no? We have discussed this
Yes, sir.
multiple times.
Okay.
The
Then, sir, R naught 1 plus beta.
right, the output resistance for cascode current mirror, the final result will be R naught times 1 plus beta. Right? So assuming the output resistance is just R naught for all the transistors for the sake of convenience, right? Instead, just you are not using the subscript, right? And let's see. So here we'll have R naught 1 is same as small R naught. That will be in parallel with R naught 2. This R naught times 1 plus beta. Now this is much greater than the small R naught. So the total combination will be just R naught, right? So then the voltage, the I naught remaining same, and RL will be just R naught, right? So we'll not have this half what we had before. So that half will just go, just I naught R naught, right? And also half will go from here, right? So that will be our voltage gain now. So the voltage gain will be just 4,000 here, right? It's twice the voltage gain. Is that clear? Any question?
Answer clear.
Yeah. So in this case, the lower the differential amplifier part, so that has the low output resistance compared to the cascade current mirror, and that is the you know the deciding factor in determining the overall gain, right? The output resistance of this differential amplifier. If you can increase this output resistance further, then you can further increase the gain. And there are multiple ways of increasing that. We can add emitter resistance, right? You can reduce the bias current, or you can use the cascade configuration for the differential amplifier. So differential amplifier also has the cascade configuration. Did you know that? No, right? So that is interesting to see the cascade differential pair. So that we can show like this. So that is our differential amplifier. with cascode configuration. So this part of the differential pair, that is how we call cascode differential amplifier. So the Q1, Q2, these are in common emitter configuration. Q3, Q4, these two are in common base configuration. Is that clear, guys? Okay, so like VID here, we will have VID by 2, right? Plus minus, here you have VID by 2, plus and minus. So you see the current here is flowing GM VID by 2, and this here flow up, right? So there is emitter current and the collector current GM VID by 2. So you'll have just alpha here, assuming alpha to be almost same current will flow, and this current also same, right? Any question, guys? So we have this the cascode differential amplifier connected with the cascode current mirror, which is working as the load for this differential amplifier. Now R01 will also change, like R02 and R01 in this cascode configuration. Here the load resistance, the output resistance will be also R0 times 1 plus beta. So here one thing I have missed, so you need to apply some bias voltage here, right? At the base, there should be some bias voltage. Yeah. Okay. So the parallel combination of these two will be just half of what we have for each of these. So the parallel combination will be half R0 times 1 plus beta. Is that clear, guys?
Yes, sir.
Yeah. So the voltage, output voltage I0 RL. So we have half I0 R0 times 1 plus beta, right? I0 is GMVIT, so we have half GMVIT times R0 times 1 plus beta. So that will be your the voltage, the gain, V0 by VID. So that will be, oh yes, do you guys this one? So now that will be half GM R0 times 1 plus beta. GM R0 will be VA by VT. So we have VA divided by 2 VT times 1 plus beta. So VA, assuming 100 VT 0.025, and assuming beta also 100, right? That will give you about 2,000, about 200,000, right? 200,000. Guys, any question?
No, sir.
Clear? Okay. So that is our ultimate circuit, right? Looks interesting, right?
Yes, sir.
Yeah. So just with transistors, right, with no resistor, right, and we can get such a wonderful circuit, right?
Sir, how to control this gain?
Hmm?
How to control this gain?
How to control? Hmm. Control is later.
Okay, sir.
So here you have this current mirror circuit, right? Sorry, the current source. So this part you can now replace with the real current source circuit. And, so this goes to plus VCC, and this is our R, and that will be our minus V. Yeah, Q9, Q10. So here now, okay, what's time? Okay, so okay, let's say this is our Q10, let's say Q11, Q12, Q13. This is so what's this stage, this Q12? Can you identify this one?
Sir, Q12.
Yeah,
Sir, DC voltage level shifter.
right. So this one here, so that is a DC level shifter. And Q13,
So Q13 looks normal common
no,
collector.
this common collector output stage, right? This common collector output stage. And what is Q11 here?
Sir, gain stage.
What is the configuration here?
Sir, common emitter. This is emitter.
This is RE1,
Yes.
right? So is the configuration
Sir, common emitter with RE,
common emitter?
with emitter resistance.
Are you sure?
Oh, sir, what will be in the collector side?
Yeah. So first of all, what will be configuration here? Why you are taking?
Then common collector with emitter resistance.
This common collector, because the input is coming to the base and you are taking the output from the emitter. So there's a common collector configuration. So this is not a gain stage, rather this is just a buffer stage. So you see buffer stage. And why we're using this buffer here? Because see that we have an output resistance here, right? Let's say this is R01, right? And the gain depends on this output resistance, which is the output, the voltage here. Let's say this is our V01. So as we have said, V01 will be the current, which is GMVID, and times the output resistance R01. Now R01, we have shown there's the parallel combination of these two, the two output resistances, and that was half R naught times 1 plus beta, right? So it's quite high, and because of this high output resistance, we get a high gain. Now we are going to the output side, and output side will have the DC voltage level shifter and all these stuffs. So, and the DC voltage level shifter has, and let's say these are the input resistance of the DC voltage level shifter, which we call Ri3. Now that Ri3 will be how much? That will be, let's say, R pi, right? R pi 3 is for this one, and
Better
plus Re, right? 3 and beta plus 1, right? So that will be the input resistance. Now, that will come in parallel with this one, right? Now, the output that will like the load resistance for this differential amplifier. Now, when you take this R01 in parallel with Ri3, right? So since R0 is 1 is much larger because you have R0, right, times beta plus 1, which is in about 100K or something like that. But Re3 will be much smaller, right, few kilo ohms. So obviously, your output resistance will be much small. Total effective load resistance will be much smaller, which will be mostly determined by Ri3, right? So, and that will lower your gain. Whatever you have achieved the gain by introducing this cascode configuration, that will be lost, right? Because of the low input resistance here. So if you can increase this resistance, right, then that will increase the total, the effective load resistance and maintain high gain. So that because of that, we introduce this buffer, right, to have a high, further enhance the resistance here. So let's say this is Ri2, and here you have Ri3. So Ri2 will be, right, the here you have Re1 and parallel with Ri3, and that times beta plus 1. Right? Is that clear, guys? So in order to maintain the high resistance, right, we put this, insert this common collector configuration here, and this Ri2, right? And so that high gain is maintained. So you're asking about this. Now this has to, you have to connect to a current source to supply the bias current. No, that will be all connected. Right? Let's call it Q15. So all the bases are tied together. Any question?
No, sir.
How do you control the gain, right? That was the question.
Yes, sir.
Okay. So that is our a simple op-amp based on our knowledge that we have learned so far. Okay. So the op-amp circuit here, like we have two inputs, right? One is our V1, the other is V2, right? And then we have the output, right, V0, and then it has two supplies, right? One is we call V plus, the other is V minus, right? Now, in between, you can have different, right, structure, different configurations for different input resistances, output resistances, or the overall gain, right? So that is our basic, let's say, op-amp, right? And in op-amp, what do you do, right? So in this case, basically, this is our plus terminal V1, and V2 is our minus terminal. So if you call this one your V1 and this is called V2, V2 is the minus terminal. So what we do, we connect two resistances here, right? This we call R2 and R1, right? And V1, you apply the signal and the closed loop gain of this one. What will be the closed loop gain?
So 1 plus
No,
RL.
it one. So if this is in non-inverting configuration, 1 plus R2 by R1, or you can ground this side and apply the voltage here. So that is how you control the gain. Did you get the answer?
Yes, sir. So we learned another thing that is called virtual short circuit. So can you show where is that virtual short circuit?
Virtual short circuit between V1 and V2, no? When you apply the feedback. So this is, okay. So we connect R1 and R2, this is V2 is negative. Okay. So maybe I can show it like this. Right, so that is how you apply feedback.
Yes, sir.
Yeah. And virtual short circuit occurs between V1 and here V2, right?
Yes, sir.
Now you can also construct this op-amp circuit using if you're discrete amplifiers and try it out. Okay. for improved performance, better performance, we can add the beta helper circuit here. Right. That will be our Q16. So that will reduce the error due to finite beta. We have number of stages. And these different stages will need different amount of current, right? The current requirement will be different. So let's say this is our I1 here, this is I2, right? This is I3. So one way to achieve this is to use different size of the transistors. Use different size of the transistors. And other way is to, we can also introduce we can introduce emitter resistance and use different values for the emitter resistances and have different amount of current. So that we discussed in our one of the previous lectures, how we can have different amount of current by using different amount of emitter resistances. So here you can have emitter resistances. So let's say you have RE, we have RE2, and so let's call it RE3, RE4, RE5, RE6. So you produce one current here, right, that we call I. And this current I will be reproduced, but at a different amount. That will be determined by the ratios of these resistances RE3 to RE4 or RE5, RE6, right? So to produce a higher amount of current, let's say if you want I1, if you want I1 to be same as I, then you just choose the same value. Or like let's say I2, you want a little bit higher value. So let's say you want I2 to be twice of I1, so you choose RE5 half of RE3, right? Or if you want I3 to be 10 times of I, so you choose RE6 1/10 of RE3. So that is how you can also get different amount of the bus current produced at different levels. And that will also reduce the error due to the finite output resistance, right? Is that clear, guys?
Yes, sir.
And the output stage is very critical. And I mean, you choose the output stage, the rating of the transistor used, depending on the current voltage power requirement of your load, right? If you need very high currents in the range of ampere, right? So then you have to use a power amplifier, maybe a Darlington pair, right, at the output stage. That depends on the power requirement of your. Usually, Darlington pair will be suitable. Any question, guys?
Yes, sir.
Sometimes the op-amp that are available, usually they have limited power capability, right? The current voltage it can go about yeah, up to 20 volt maybe. So that's good enough. But the current is very small, about 20 milliampere maximum, or can get a little bit higher current. So if you want a higher output current than your op-amp can provide, right? Then usually you add another the power amplifier, right, and the output, right? So you can use a power amplifier. That will be in common collector configuration, right? So if you use a power amplifier common collector configuration, that can provide, maintaining the voltage level, but can boost the current, right? And giving you the power or the current that is needed by the load. So that was the actually the our one last topic for this for our course, the power amplifier. But we don't have time to cover that. So how to design a power amplifier. Right? But for time being, I mean, just for your knowledge that you can use a power transistor in common collector configuration at the output of the amplifier, right, to boost the level of the current and the level of the power. Okay, so that'll be all for this course.